Hello there. Welcome to this video lecture on heat integration, pinch technology, minimum number of utilities, minimum number of heat exchangers method, part 1, introduction and choosing a minimum approach temperature. I'd like to start off by asking you to identify the difference between these two designs. You might have noticed that for the first design, the reactor inlet is heated with high pressure steam and it is cooled with cooling water. In contrast, the second design takes the reactor effluent and uses it to heat the reactor inlet, after which it is cooled with cooling water. If you were to ask me the difference between these two designs, I would say that it's probably about $5 million over 30 years. And this is because this design saves money on high pressure steam and cooling water. So why do we study heat integration, pinch technology, or minimum number of utilities, minimum number of heat exchangers? It's because recycling heat makes a big difference in terms of the bottom line. So what is heat integration? It's all about finding matches between hot and cold process streams as much as possible so that you don't have to use steam, natural gas, or cooling water. This saves a lot of money. In this video lecture series, we will cover the 6 steps in heat integration. The first step is step 0, making sure your process is optimized. Step 1 is choosing a minimum approach temperature. We will choose 10 degrees centigrade. Determining which streams need to be heated or cooled and writing down their flow rate times heat capacity, inlet temperature, outlet temperature, and overall heat. Constructing a temperature interval diagram. Constructing a cascade diagram, which helps us determine where we have pinches, which we will cover later. Determining the best arrangement for heat exchangers is the last step. One of the most important aspects of learning heat integration is to not expect that you're going to understand it the first time around. I didn't understand it the first time I read it in several textbooks. Try to trust the process and don't get frustrated. The example in this video lecture series is based on material presented in the pinch technology chapter of the Turton textbook. So if any part of this is confusing, perhaps reading that part of the textbook can help. Step 0, as mentioned before, is making sure your process is optimized. This means that you want to make sure that your streams are at their optimized temperatures, pressures, and flow rates. So this is a process flow diagram I developed. It is an optimized process flow diagram, but you might notice there's no heat integration. But I know that every flow rate, every temperature and pressure are exactly what I want it to be. The separations are exactly optimized the way that I want them to be as best that I can. And so now this process flow diagram represents a diagram that I could use for heat integration because I've optimized it as much as possible. Optimizing your process after heat integration is very, very painful, time-consuming, and difficult, so try to avoid doing that. Step 1 in heat integration is choosing a minimum approach temperature. Before we do that, we have to state some definitions. A hot stream is a stream which has heat to give, which means that the stream starts off hot. A cold stream is a stream which needs to be heated. In other words, it starts off cold. So this is an example of a hot and cold stream going through a heat exchanger. The hot stream starts off at 200 degrees and at the outlet is 100 degrees. The cold stream starts off at 90 and exits at 165. Notice that these lines don't touch, they don't cross. There's a minimum temperature difference between these two streams at all times throughout the heat exchanger. So this means hot and cold streams coming in or leaving a heat exchanger need to have at least 10 degrees centigrade temperature difference. At any given point in the heat exchanger, a cold stream cannot be less than 10 degrees cooler than a hot stream. So in other words, these lines cannot cross. The hot stream must always be hotter than the cold stream. So we will choose a minimum approach temperature of 10 degrees centigrade throughout this entire example.